So let's do a quick recap of what we were talking about last Thursday. I know you have a Math AS assignment due tonight that has some to do with the two different methods of rate of change approximation and some other things about fundamental theorem. We're going to be talking more in depth about both of those today. We've talked about the stuff that's on the homework, but the things we're going to talk about today will maybe help solidify that if it's not quite making sense yet. So on Thursday, we were talking about two different ways to approximate rate of change. And so our first method that we talked about, and it's not like one's a bad method and one's a good method. They just lead to slightly different types of results. So the first method we tried about was just exactly reversing the process that we had been using prior to your first test. That is, I have this idea of an exact accumulation function. Or in this case, it could be exact total accumulation or net accumulation. The graph happens to start at the origin. So let me pause this for a second. When I have a small value of x, so this first one, I have this set to have intervals of width 0.4. And so for all x values between 0 and 0.4, what I'd be doing is trying to make an approximate accumulation function that has one constant rate of change throughout. So the method that we went about was say, okay, so if we set this interval size and a starting point, so a, lowercase a equals 0 and delta x equals 0.4, then between 0 and 0.4, let's see if I can get this to stop right at 0.4. Close enough. So pretend this is exactly at 0.4. It's at 0.39. So between x equals 0 and x equals 0.4 here, instead of having this curve with a whole variety of different steepnesses indicating rate of change of y to x, that ratio, I'm going to have one rate of change. So I want a constant rate of change that accomplishes the same amount over this interval. It's called an average rate of change. So I use the average rate of change over this interval, which is found by finding the slope of the secant line that connects the endpoints here, the 0, 0 to 0.4 comma f of 0.4. And if I find that rate value, if I were to try to sketch this rate graph using this method, then over that first full interval, 0 to 0.4, I'd have one rate throughout, because that's how we're constructing this. So that instead of having a whole variety of rates between 0 and 0.4, I have one rate that's found by using the coordinate points of the exact accumulation function, net or total, this one could be either, between its endpoints at x equals 0 and x equals 0.4 on this function. So if I were to look at the rate graph before this point, it would just be less of that straight line. It's not different values, but between x equals 0 and x equals 0.4, I have one rate. And then suddenly, at 0.4, we change, because we change intervals here. So the next interval, interval number 2, thinking about our summation, this would be like j equals 2. During interval number 2, which goes from 0.4 to 0.8, I'm going to move out a little bit so we can see more of it. I'm going to use the steepness of the line segment that connects, if I can get it, that connects x equals 0.4 to x equals 0.8 coordinate points on that curve. And since the curve isn't particularly changing too much, it's slightly curved downward, but that line segment, it's very hard to tell apart from the curve there, but there is a purple or magenta colored line segment here in any case. And its steepness, its slope, ratio of change in y to change in x, is about, let's see, looks like 4.5 or so, according to where this is over here. Easier than trying to estimate x and y coordinates here. But so according to this rate function here, it's about 4.5 or so, as opposed to around 14 for the first interval. And as we go on, we get different rate values for each interval, although this end section of this accumulation is going up slowly. Thinking about what we did with the Usain Bolt question a long time ago, now his looked more straight line-ish than this does, but the rate of change that we computed over at various points at various small intervals changed a little bit in that, and it changes a little bit here, but you can see the rate values, again, they start at 14 and then down to like 4.5. But after that, they're all between like 2 and 4.5 or so. It's kind of smaller, slightly smaller, slightly smaller, which should make sense. Smaller rate values, less positive, because this graph is getting less steep. So just visually, even though we don't have a function formula to work with on this, a rule to work with, it should make sense that the rate values as they go out are being estimated by smaller and smaller quantities. Now the issue is, this isn't a particularly great approximation, especially between 0 and 0.4. After that, it's actually not that bad, but you can see this rate function here is nowhere close to a normal looking function. It's just piecewise constant. I've got a bunch of different separate numerical values. But as we talked about, we can describe this rate function with a single formula, because to find the values on it for any current value of x, no matter what interval x is in, I do the same thing. I find the left and right end of the intervals that x is in, which would be f of left of x and f of left of x plus the interval size, plus delta x, like left of x plus delta x as the input to f, to find the two y values, because the x values are left of x and left of x plus delta x. Now I have h's in here just because it's impossible to get delta x's to show up, but we also are going to use h for something else in a moment. So this idea of find the left end of the interval, find the right end of the interval, and find the slope between them results in a formula like this, with this left of x, where left of x, again, was kind of a function that's our shortcut notation for that a plus the floor of x minus a over delta x, all times delta x, and it's really tedious. So besides the fact that it's not quite the sort of rate function we're looking for, I'd like something that, even with h smaller, I'd like it to connect instead of just being a bunch of different rate values that always are going to change suddenly from one to the next, because of the way we do this. The second I moved into a new interval, I have a completely new computation to do. Because of that, we're going to use a different structure for doing a very similar thing and get similar sorts of rate results, but we're just going to set it up a little bit differently. So differently from exactly reversing what we've done going forward. But in the end, when we have small intervals, it has the same resultant shape or pattern of values. It's just that they end up, because of a different construction, being able to be connected. Because instead of relying on inputs of left of x, it's going to rely on inputs of just x. So since x is just a normal variable, as soon as x changes a little bit, x changes a little bit. So f of x changes a little bit. It doesn't depend on the size of the interval. I'm going to have a set of rate values that change no matter what interval size I have, whether it's large or small, continuously as x changes continuously. So as x increases from 0 to wherever, or I could even talk about x decreasing, doesn't matter what direction I'm going in reality, I'm going to get a smooth set of changes in this rate value, as long as this function here is something smooth. Now, if this had a corner, points where there is no rate of change, those vertices or wrinkly functions, then there's nothing we could do about it anyway. But to set this up in a different way, if I imagine having, let's see, if I can get this to a reasonable size, there's an h of about 0.3. If I imagine, instead of having preset interval locations, if I have an interval that's a fixed width, but always travels in front of x, I can always do it behind x also, just kind of like the left versus right. It's just a decision to make that doesn't have an impact on the end result. But if I imagine just finding the steepness of this line segment, which is a secant line that connects 2 points of this function, as I travel from left to right, I'm going to refer to the steepness of this line as the rate of change in the moment where x is. Now, if I have a larger h versus a smaller h, it still can be a worse or a better approximation. But you can see that just because you can see this line's steepness smoothly changing, not suddenly changing from one value to a next. So the steepnesses are graphed in the left. Just a visual of what the steepness is what we're seeing on the right. So we're not actually writing any equation for this blue line. We're just graphing its slopes as x travels. So this isn't an exact rate of change function right now. I've got h equals 0.3. I know, for instance, right near the beginning here, just like before, that function f isn't doing exactly the same thing as this straight line is. I can even see the space between it. So this isn't an exact rate value that's given over here, but it's an average rate of change over that small interval. It's just that when I move x a tiny bit, I get a new interval entirely. No matter how, even though my h is 0.3, if I move x by the smallest amount, I have a new interval that's still 0.3 wide to work with. It starts at a new x and ends at a new x final. And then the slope is going to be something different. So it changes smoothly as x increases, unlike the preset intervals where when I move into the next interval, I suddenly have a different computation to do. This one changes just along with x. So I can make a better approximation, just like we've talked about before, by making h smaller, because if I have this smaller interval, it's going to be less far off or less of an approximation of what the steepness of or the rate of change of function f is. So let me pull up one last thing here. This red curve here is the exact rate of change function. If I make h larger versus smaller, it's got the blue graph has the same type of shape, but you can see as h gets smaller, the shape of it gets closer and closer to, let me freeze this, the shape of it, h large versus h small, and h as small as I can program in here, 0.005, you can hardly even tell the difference, even at this beginning part. When I know that the beginning of this caused lots of problems before, when I have h incredibly small, I have this smooth function still that does match up pretty well with, at least in the field of vision we've got here, pretty well with this idea of the exact rate of change function. So the exact rate of change function is, well, we're doing this operation here. So instead of worrying about where are the intervals starting and stopping, my intervals are always starting at x and always ending at x plus h for every value of x. So it's not a set of intervals that you can count. There's going to be infinitely many different intervals that are used, but the expression here, f of x plus h minus f of x, that's that y2 minus y1 over, well, the width of the interval, x2 minus x1. It's just a general slope computation. Just instead of expressing with numbers between two specific points, this is for any particular value of x I want to pick. I'm going to use my x value, and I'm going to use a value h units for a generic value of h to the right of that, so x and x plus h, and then find the slope or the ratio of the changes in y to x, vertical to horizontal, dependent to independent, whatever terms make most sense in your situation. I'm going to find those ratios of changes, and that gives me my rate of change value for any x value. But if I leave it as a general x and a general h, I can think of this as a formula to construct a rate of change function as opposed to just a rate of change individual value. And this rate of change function, when h gets smaller and smaller, becomes more exact. And if I can imagine h essentially 0, it can't be 0 or there'd be nonsense. H essentially 0, meaning I have to have a small amount of change in my independent variable for there to be a rate of change. But if I can imagine h essentially 0, which we did at the end of class on Thursday last week, and we're going to recap today, then I can compute actually a closed form, normal looking sort of formula in a lot of cases, not every case, sometimes it's still kind of a mess and we can just express it, that you can use to find particular numerical values for any moment x that you want. So let's kind of recap what we did then at the tail end of class on Thursday, and then we'll get into fundamental theorem of calculus stuff. Let me just open up a new window. Do I have a, here, blank one. So what we talked about was, all right, so our formula that we're going to use to find a rate of change function that's the sort that we want, a continuous sort of connected function that when h gets smaller, I don't have a bunch of separate numerical values. I have a set of connected values that form a function. So r sub f of x, the rate of change of function f with respect to x, involves two values of the function, f of x plus h and f of x, the right end and the left end of a general interval. So this is like finding the slope over an interval x through x plus h. So thinking about this interval, it starts at a general x and ends at an x plus h. There's my change in the dependent quantity. X plus h minus x is going to give me h. And then all I do is imagine that h is essentially 0. Not exactly 0. Sometimes you'll see this symbol. Sometimes you'll see the like approximately equal that way. It means the same thing. Essentially equal to or approximately equal to, but not equal to, just approximately 0. Because without h having some size greater than 0, this is nonsense. So the two functions that we looked at on Thursday were related to geometry things. So we had area of a square was given by x squared. And if I want to know at what rate does the area change relative to side length changes, area is given by a of x, x would be the side length of the square, the rate of change of function a with respect to x was given by, well, I do a of instead of f of, this function happens to be called a of x plus h minus a of x all over h. And the only messy part to that is this a of x plus h part. I mean, a of x is x squared. It's just the first part of the numerator that's a little bit of, it's just algebra. This isn't anything, this isn't calculus here. This is just algebra. It's just slightly unpleasant algebra. And all it is, oh, a of x is x squared. A of x plus h is x plus h quantity squared, which you have to remember is not just square the two parts, it's distributive property. So it works out to be x squared, 2xh, and h squared as the three terms of expanding that, and then minus x squared. And we can do some more algebra. The only part of this that's calculus is done by the time we get to here, or maybe here, if you just want to call it copying it down. That's all the calculus. The rest of this is just algebra, algebra 2 sort of stuff. It's a little bit tedious, but I don't want to spend a lot of class time on simplifying. I know you're going to talk about some of that in your recitation this week, just some simplifying and rewriting algebra review, because without it, if you forgot it, it makes some of the things we need to do a little bit messier. But just continuing simplifying this, 2xh plus h squared over h, just by canceling out the like terms, is reducible by a factor of h. So we get 2x plus h. So all this is r sub a of x, as long as I make h essentially 0. But I can see in this form, in this simplified form, it's a little hard to see here, that if h is essentially 0, it looks like that causes a problem because denominator h. But after expanding, factoring, reducing, whatever, see, oh, well, if h is essentially 0, then r sub a of x is essentially 2x. So r sub a of x is 2x. When I have this h value essentially or approximately equal to 0. And so I say that this function here is the rate of change function for function a. This is the kind of just written out definition. This is with the specific function plugged in, and then all of this is just some algebra to simplify it. There are multiple notations for this. Rate of change of function a is written like this. Using our dy and dx, since it is a ratio of changes in y to x when we're talking about extremely small changes, I can also say that. Now y wasn't specifically used here, but a is the dependent variable, so it's equivalent to this. So sometimes you'll see something like this. To make it more match up with the notation of this formula, sometimes instead of writing y on the top, you'll see dA of x, dx over dx. Any of these? One other symbol that's less descriptive of what's going on, but it's just to simplify the way that you can type this on a keyboard or on specifically a typewriter, is instead of, because fractions, if you don't have a computer, if you just have a physical typewriter, are really annoying to try to make people understand what's in the top and bottom. So another notation that's also used for this comes from old typewriters, just, oh, I'm going to call this A with a little mark like that, meaning it's related to function A, but it's not function A anymore. So all of these mean the same thing. They all indicate the same, this is going on. We're finding a rate of change function that's valid for any x in the domain of function A. And all of those notations are telling us the same thing, and it's just a new function. So it's a rate of change function. It's also sometimes called less descriptively, but very commonly, a derivative. Derivative just means it is derived from, it's something that came from this other formula. But this derivative, all a derivative is a rate of change function. The word derivative has multiple meanings, but in a math context, it almost always refers to a rate of change derivation. So this little mark here means that I've done something to function A. This is no longer function A, this is function A's rate of change. This is a kind of generic description. If you have like a y equals sort of formula, dy over dx is often used just because it's just, there's no description of what is y, what is x, it's just the general y's and x's. Let's see, is there something else? If it is just a function called y, this one happened to be called a. If you just have y equals blah, 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 you might see y prime equals. It doesn't have to have an of x for this little mark to be used here. By the way, I just said that. Prime is how that's usually read, not like a apostrophe or something. When you see that a and then that mark and then x, that's typically read as a prime of x, and it just means the derivative of or the rate of change of a with respect to x. So all of these say the same things, and again, all of them just mean rate of change of, or the rate of change of the dependent with respect to the independent. Visually speaking, it's about steepness or slope. So these are models for the steepness or slope of, specifically, a of x equals x squared. So let's talk about that. All right, so if I have a of x equals x squared, and the rate of change of a of x with respect to x is given by 2x, that means, visually speaking, I'm on GC, I should almost just graph this way. I want to do it kind of manually. So y equals x squared, boring parabola, right? I'll pretend that that's symmetric, but it has points on it, like 2, 4. I'll pretend this is -3, 9. Just a few points. 0, 0. There we go. What this tells us, I could graph y equals 2x, but if this is talking about area of a square, x would be maybe in centimeters and area in square centimeters. This wouldn't have the same y values because this is talking about rate of change. This would be the y units on this. Input is still x. The output is the rate of change. Or maybe it's more clear in this other. The rate of change of a with respect to x is 2x. So x is the input and a rate of change is the output, or the independent variable would maybe be centimeters, and the dependent variable for R of A would be how much the area changes, square centimeters, per centimeter. And I don't really want to reduce that to centimeters because that sounds weird, but it is square centimeters in area per centimeter in side length. That's what the units on this would be. Whereas the units on this are independent centimeters, dependent square centimeters. It doesn't have to be centimeters, so I was just using that as an example. So they wouldn't have the same input and output, so graphing them on the same axes would be kind of weird. That's why we always have the two separate axes when we've done the rate functions and the accumulation, because they're talking about dependent quantities that are completely different things. But if I think about, remember the line that was kind of following along on the animation that we just had up here? If I think about rate of change function, if I want to know what's the rate of change of function A, at this point, well, it can't be at a single point because I can't have h exactly 0, but I can imagine in this moment, in the moment when x is 2, so 2 through 2 plus h, as small as h as I want to have, what's the ratio of changes? Well, it says it's 2x. So at x equals 2, that means this rate, or the ratio of y to x changes, is going to be 2 times 2, which happens to be 4. Same number, but this 4 is talking about square centimeters in area per centimeter side length. This is talking about, well, when the side length is 2, the area is 4 square centimeters. So to make this point, look at this over here. If I'm looking at this point, still the same function for the rate of change of area with respect to side length. If I'm at this spot at x equals -3, the rate is supposed to be 2x, right? So 2 times -3, so -6. That's not saying that the y value there is 9. It's talking about, now this doesn't make sense for a square area, but just thinking about this function in general, it could represent other things. With this x equals -3, if I vary just a little bit away from -3, the y value changes by 6 times as much and in the opposite direction, negative. So another way to think about this, within that circle there, if I connect 2 points within that little circle, I'm going to have a slope of about -6. If I connect 2 points within this circle, I'm going to have a slope of about 4. What about around the vertex of this parabola? What would be the value of the rate when I'm in the moment where x equals 0? Yeah, it'd be 0. So this is saying, again, if you want to think of it, like if I connect a couple of points on the curve within that small circle, that small moment around x equals 0, the derivative, the rate of change of y with respect to x should be about 0. Is it going to be exactly 0? Depends on what points I pick. But at the moment where x is 0, the rate is supposed to be 2 times 0. So that's 0. Or in terms of the lines we were graphing, like I said, if I were to connect 2 little points here within that circle, the slope would be about 4. If I connect 2 points inside that circle, the slope's going to be about 0. And if I connect 2 points in this circle here, the slope's going to be about -6. That's what that rate function visually is telling us about. The meaning of it, not like the left half of this doesn't make any sense for square area, but the meaning of this is about rate of change. So we have a formula that we can use values of to compute rate of change as numbers, but we can use it for any value. So we can also talk about the patterns of these rates of change. And so if I think about, well, this is a linear function, right? If I were graphing x and y, if I graph y equals 2x, I want to use my other notation, a prime of x. Well, at 0, it's got a value of 0. At 2, it's got a value of 4. If I were to go back to -3, I'd have a value of -9, and so forth. The y values, if I were to graph this separately, would indicate the same thing as the slopes on the original graph do. So there's different ways you can visualize what this is telling us. But that aside, we've got a task to do over the next like, let's see, this week, and then the week after spring break, and maybe another extra day after that. And that's to learn how to quickly start from an accumulation function like this and get these derivatives or rate of change functions because they follow patterns. So let me just pull up, let's see. So we did last week, let me rewrite the one we just had and then the other one that we talked about. So we had a of x was this area of a square. And so to use our, this is kind of the fastest notation to write also, to write the derivative of this, it's 2x, meaning this is our rate of change, is given by this function for any x value. I can find the rate of change in that moment by using the formula 2x, the rate of change of this function. So this is derived from it. The other function that we had, I left in unsimplified form at the end of class. We had the volume of a sphere, which is 4/3 pi r cubed. And in the unsimplified form, we talked about you can kind of see what the pattern for polynomial functions is. Polynomials are sort of similar sorts of functions. They're predictable based on their degree, whether their leading coefficient is positive or negative. And you even learned a bunch of things, I'm sure, in algebra about what happens if you make the coefficients bigger or smaller or negative and those sorts of things. That's actually helpful. In unsimplified form, what we did was we factored out the 4/3 pi out of that whole fraction with the f of x plus h minus f of x stuff. And then, here, I'll just separate that off in parentheses. And the rest of this came out to be 3, I wrote x and then I wrote r because I was talking about spheres. Hold on a second. Don't want to have r. Ooh, I have a big eraser apparently. 4/3 pi x cubed. I'll stick with x's. So what we ended up with was this formula. I didn't simplify it. I do want to talk about the simplified version. But if you can see this 4/3 pi, because of the fraction structure and the factor reduce quality anyway, we can factor it out. If it hadn't been there in the first place, I can maybe see if I just had a function f of x that was just plain old x cubed, its derivative, or rate of change function, would just be this part right here, 3x squared. And we talked about at the tail end of class, if I had x to the 4th, taking a guess, any thoughts on what that would be? Its rate of change function. Yep, 4x to the 3rd. So you can see this 2x to the 1st power if you want. This is actually what's called power rule for shortcuts in derivatives or shortcuts in rate of change functions. And we'll prove it later when we have some other things we can use. But basically what it says is for any power function, which polynomials are multiple power functions added and subtracted, but for any power function, meaning something of the form f of x equals a power of x, and it can actually be any power, positives, negatives, fractions, decimals, rational, irrational, doesn't actually matter. What we've seen here is just whole number powers, but the derivative of a power function is a power function that's one lower in degree. So if the original was x to the nth power, the derivative is the n minus 1st power. But as you can see, this second power ends up with a 2 coefficient on its derivative. This third power ends up with, more easily seen here, a 3 coefficient. This fourth power ends up with a 4 coefficient. So the nth power derivative, the derivative of an nth power function will have an n coefficient. So as to this, which had a coefficient in the first place, notice this is kind of tagged on, so it's multiplied on. Think about this a of x equals x squared. If I have here 7x squared, or k of x equals negative 19x squared, those are still parabolas, just like this a of x, right? Those, thinking about algebra things that you learned, those coefficients in the front just well, let's see, if it's a 7, it makes it really steep or really narrow looking. 7 times as steep, in fact. With a negative 19, it would be really steep, but it'd also be flipped over. So all the, like where it was going up, it'd be going down and vice versa. It's not just with this 4/3 pi, and we don't have to do all of these from scratch. If I want to find the derivative of j prime of x, well, it'd just be like the derivative of x squared, but 7 times as steep. So the steepness, visually speaking, of x squared is given by this 2x, that slope between 2 points. It's also just a rate of change, even if you're not thinking of graphs and shapes and things. But this makes it change 7 times as fast as without the 7 there. So we can simplify that. That's just, algebra 1 sort of thing. But it comes from just multiplying on this coefficient, because you know those coefficients alter the steepness or make the y values different than what they'd been before, just by scaling them up or down, or in this case, negating them. For this k of x, if I wanted to find its derivative or rate of change function, it'd just be negative 19 times the derivative of x squared, or negative 19 times this 2x. So negative 38x. And thinking about that, if I did have this negative 19x squared, a really narrow sort of parabola going down, just thinking of algebra stuff that you've had to do before, I'm sure, all those transformations and toolkit functions and stuff. Well, think about the values of this. If x is a positive number, this is going to come out negative. When x is positive, slope between any 2 points in this picture are going to be negative, right? Like, oh, if I'm over here, if I'm there, they're going to be pretty negative, in fact. If x is something negative, I'm going to get positive results from this formula. Well, if I look at this downward-facing parabola, where x is negative, oh, well, the slope between 2 points, like in any little tiny circle I could draw, is going to be some sort of high positive slope. And when x is 0, the vertex, again, I get 0 as a result for either of those and anything else that is the same format. So in any case, this power rule applies to any power of x in reality, not just x to whole number powers. And we'll prove that later. I'll show you maybe a little bit related to whole number powers, just kind of pattern-wise. It relates to binomial theorem, but it's just kind of it's a pseudo-proof anyway. It really comes from some techniques that are like down the line a bit past your mastery test. But this power rule is a nice shortcut that allows you to find derivatives of x raised powers. And with just a little bit of like stuff you've thought about before in other contexts, you can alter this, say, oh, well, it doesn't just have to be x to a power. It could have a coefficient also, and that's not a big deal. I'm just going to multiply on that coefficient to whatever the result would have been otherwise. So, in fact, I could have crazy looking functions like, let's see, q of x equals 7/3 x to the square root of 6 power. And that looks awful, but according to what we talked about, if I wanted to find the rate of change of this function q, which is just some sort of power function, square root of 6 is somewhere between 2 and 3. So this is slightly different looking than a parabola, but not much. It would only have, well, I won't deal with that. But if I want to find the derivative of this, well, I know this 7/3 just makes it 2 1/3 times as steep as it would be without that. And according to my power rule here, the derivative of this would have, let's see, x raised to a power has 1 lower a power. So, well, not the square root of 5, but just whatever square root of 6 minus 1 is. So instead of being 2 point something, it's 1 point something. And then multiplied by whatever that power was, square root of 6. So this is an unpleasant looking thing, but it is a rate of change function that corresponds to that lovely function q of x. So it's a derivative of the derivative of q of x. And there's not a need to simplify. I'm not going to test you on your algebra simplification of using these rules. The intent of the mastery exam, so isn't you're not going to do x plus h stuff and do all that end of algebra. I also don't want you to be doing any like sort of algebra to make this look prettier. What I want to see is, do you know these series of shortcut rules? This is one that we're going to talk about. A second one is that constant multiple. And there's a few others that are pretty simple, like what if I have a polynomial, like a couple terms added together? That's not a whole big deal either. There's a few that are trickier, and there are other sorts of functions that aren't power functions, like logarithms, exponentials, trig functions, inverse trig functions. And we're going to prove some of their rules now. We'll prove some of their rules after the mastery test because they do involve actually harder stuff, but the rules have nice patterns. But let's get back to meanings of these things. All right, don't save that. All right, looking for this guy. So we talked about the fundamental theorem of calculus. I think it was the day before, the lecture before, and the lecture after your test. So it was last week, Tuesday, and the week before Tuesday. But all this is, it's a relationship between rate of change and accumulation functions. So if I have this function f of x that gives me an exact amount or an exact total accumulation of something, whatever it is, I can find a rate of change function from it, which that's what we've just been talking about. If I have a function that tells me how much of something I have, how do I determine at what rate it's changing? Well, I find, essentially like slope computations, rate of change computations between 2 points, and then imagine those 2 points to be A, general, and B, very close together. So we had this expression, the rate of change of function f, or f prime of x, if you want to use the short derivative notation, is generated by using this f of x plus h idea, f of x plus h minus f of x, the beginning and end of an interval that starts at our current value of x, divided by the length of that interval, delta h, or not delta h, h, and then we imagine h to be essentially 0, and see if we can simplify and come up with something nice, which we generally can. But if I have an exact rate of change function, what we did prior to your last test was, oh, well, if I have an exact rate of change function, I can generate accumulation. And we can do it approximately using a summation, or as we talked about just after your test, we can find an exact accumulation, net accumulation starting at lowercase a with intervals of delta x, and then we let delta x become extremely small, gives us exact net accumulation. Starting at x equals lowercase a here, for the exact version, we don't write the summation, we write this integral. But all this means is a summing up of a rate times a change in the independent variable. So mdx sort of expression, r sub f of t times dt, using all the values of t between a and the current value of x. Lowercase a, our starting value of accumulation, and x, the current x value. We could leave it as x to have a formula. We could put a number in that position to have a value of accumulation. And again, so we've gone from an amount to a rate back to an amount, but it's not quite the same amount. This is just a net accumulation starting at some independent value of a. So if I want to have the total amount back again, I have to know some initial total amount. Kind of like if I tell you the slope of a line and tell you to write its equation, like, well, I need more than that. That's kind of what we have here. It's like, well, if the slope of a line is 3, write the equation. It's going to be y equals 3x plus or minus something. And you need to have some additional information in order to be able to write the equation. Same thing here. If I want to know an exact amount of something, not just how much is generated by the rate of change, which is all this net accumulation gives us, I have to have some starting value. And so whatever this starting value is, I can start at y initial plus mdx. So that's what this is, y initial plus using the rate. And so this could be any value of a, but I need to have it match. So the amount that I have at time a plus what happens afterward due to the rate function. If it was 0, then this would be f of 0 plus the integral from 0 to x. If it was time negative 17, I could have f of negative 17 plus an integral from negative 17 through x. any value you want, but whatever you have, whatever one starting or just some kind of point to tie this down, whatever this one value of the total amount or total accumulation function you have is, start there, and then you can integrate onward using the rate function to indicate the changes that happen after that because of the rate that we know about, the rate of change that we know about. So just rearranging as before, that bottom line said f of x is f of a plus that integral from a through any current value of x you want, or just leave it as x to have a function. This also means that if just algebra rearranging, subtracting f of a from both sides, I could write this, which this alternate, these are the two general forms of the, if you look up fundamental theorem of calculus, you're going to see these two different rearrangements. F of x minus f of a is this integral from a to x. So you can also think of that as y final minus y initial, change in y overall between a and x, is generated by using that rate between a and x. That should make sense also. It's just a different formulation of it. Instead of thinking about generating total accumulation values, you can think of it as generating net change between 2 points. So I could use numbers in both of those spots, and typically when we're talking about numbers, we're not going to use x. So instead of a through x, if I call it a through b, that sounds more like, oh, a and b are kind of equivalent. They're both specific individual, they're both parameters indicating a single value. So this is how much change is generated between independent values of a and b, like y final minus y initial, using this integral notation here. So these are all just rearrangements of the same fact, the same putting together of total accumulation f of x, just by just algebra or thinking about, well, what if I put in a number for x instead of leaving it as x as a function? But they're all telling us kind of the same thing. So let's use this on our sphere thing that we talked about. So, oh, I never did write out the simplified form of it. 4/3 pi x cubed. I'm going to have to click around here a little bit. 4/3 pi x cubed. We came up with its derivative was, let's see, r sub v of x equals 4/3 pi times 3x squared. If you do simplify that, I've got an x squared. I've just got a couple of coefficients, 4/3 and 3, that I can multiply instead of having two different numerical coefficients along with that pi irrational number coefficient. The 4/3 and the 3 are easy enough to combine to make a 4. Now, the reason I wanted to simplify this was just actually for a side note. If you recall geometry, 4/3 pi r squared is a geometry formula. Do you remember what it's a formula for? Not a cylinder. It's something definitely round, but it's not volume of a sphere. It's a formula that's less used, but 4/3 pi r squared is actually the formula for the surface area of a sphere with radius r. So, strangely, but not actually coincidentally, if I have a volume and I want to know how it changes, the way in which it changes is related to the surface area. So as I increase, if you want to think of it this way, if I have it like, think of a gumball. If I think about the volume of a gumball, and then I paint on an extra layer of like candy on the outside, increase the radius just a little bit, how much did it increase by? It's related to how big that surface area is. The surface area amount of like painted on candy shell, that's actually a little bit of extra volume, but the volume is related to that surface area that I had to cover. So it is actually related, just kind of side note fact here in case that looked familiar. But geometry does that a lot. It works better with spheres than it does with polygons and round circles. If you do the derivative of a, let's see, area of a circle is pi r squared. The rate of change of the area of a circle, according to our rules, well, keep the coefficient, and the derivative of, oops, I wrote r out of habit of geometry. derivative of x squared we said was 2x. Well, this is maybe not written in the normal letters or order, but 2 pi r is a formula for what related to a circle? Yeah, 2 pi r is the circumference of a circle. If we take the derivative of the area of a circle, or think about how does the area change when I increase the radius, the area increases are related to the circumference, or the distance all the way around. So, again, not actually coincidence. It's not going to help you solve a lot of problems for right now, but it actually is kind of useful stuff. And it's not just random magic of math. It is actually related to how shapes work. All right, so let me go back to fundamental theorem here. So we have the volume of a sphere was 4/3 pi x cubed, or use r if you like it better. And so we found the rate of change was 4 pi x squared in that simplified form, multiplying the 4/3 coefficient and the 3 that we ended up from power rule, or actually our algebra that we did. So because I know the rate of change of the volume, I can reconstruct the volume formula, even if I didn't know this up here. I could reconstruct the volume by saying, oh, volume would be some initial value of volume plus whatever happens due to the rate. So this is my r sub v of t dt. Just using, I don't want to use x in too many spots. And this looks like a mess, but this is true for any sort of case. If I have a rate of change function, I can generate accumulation with it, writing this integral notation, and get total accumulation by taking any starting value. Maybe with a sphere, it'd be easy to say 0. Oh, volume of a sphere with radius 0 is 0. So I'd have 0 plus integral from 0 to x. Should give me this. So v of x, this formula up here, is equal to 0 plus this integral from 0. Or you don't have to use 0. You could use any value of volume that you want and the corresponding x value that gave you that. But based on the other rearrangements we talked about, if you wanted to see how much different the volume of a sphere with radius 7 and radius 2 is, we have a closed form function up here for volume, but just thinking about rearranging this and using specific values of beginning and ending of accumulation instead of x as a variable and a as a generic parameter start, say, oh, well, final minus initial, v of 7 minus v of 2 would be this, integral from 2 to 7, where we just accumulate the area, or this just gives us the extra volume because of that change in the radius. We don't have to calculate out the separate volume amounts and subtract them. This expression does all of that in one. This gives us the amount of accumulation between radius 2 and radius 7 because of that rate. Without writing any other things, without computing anything else, this gives us a value. You could type that into GC and it would give you a numerical result for that. It's just tedious to do by hand. All right, so let's go back to calculating rate of change functions. And let's say that I'm looking at this function g. I just gave you a couple of points on it, not the whole function rule. But if I wanted to approximate the rate of change for g in this area of the graph, this is a pretty big section. It's like h equals 3, right? From x equals 1 to x equals 4. But if I wanted to estimate the rate of change, it's just ratio of changes y to x. So y final minus y initial over x final minus x initial. So that shouldn't be too hard, I hope. 2 minus 4 over 4 minus 1. So negative 2/3. So this is a h value, interval width of size 3. And so this rate of negative 2/3, that's just a, did it on the calculator or GC or something, maybe you get the decimal, like, oh yeah, that's negative 2/3. Negative 2/3 would be the slope exactly of that purplish line, which as an estimate an attempt to recreate G, but very poorly, right? Just big enough so we can see it easily. Now, think about this. If I were to ask you about the steepness of this graph in the moment where x is 1, I know it's not exactly this negative 0.667. It's not exactly negative 2/3 either. If I were closer to the moment, if I use a smaller interval, what would my number be like? Would it be more negative or less negative than this negative 2/3? More negative, right? Like I can see by looking around x equals 1 that the actual black curve is going down more sharply, more change in y per x in a negative direction than the purple line has. Or if I ask you the same about what's going on around x equals 4, around x equals 4, x is changing, like the ratio of changes y's to x, function g is going downward less steeply than the purple line is, so be less negative at this point. This is an average rate of change. We don't find average rates of change by averaging a bunch of different rates of change. We just do this, it's a continuous set of numbers, so we just use the endpoints and generate rate of change over an interval. But it is average in the same sense that this average is too high, not negative enough, to represent this point, and too low, meaning too negative in a sense, to represent that point. It's in between though, so it's a representative slope or steepness or rate of change for that interval. So if we want to get a better value, we look in closer. So here's the actual function rule that we've got here. You can see that 1, 4, and 4, 2 are two correspondence points on this. But let's say that I want to use these 2 points instead. And I'll just do decimal forms. If I wanted to find this h equals 0.05 slope, that would probably be much more accurate, a representation of what's going on around x equals 1 than the purple line is. Agreed? I mean, I could still make it better by picking closer points. But these two, if I look between those 2 points, thinking about what we did with the Usain Bolt graph, like, oh, yeah, that between those 2 points, this looks kind of like a straight line. It's going down. It's definitely going down more quickly than this purple line was, and we could do a computation that gives us this negative 1.3, which, again, if you're doing numerical computations, make sure the results make sense. That should make sense. It's much more negative than the negative 2/3 that we got from the original large interval. So just keep in mind what this means. It's not just about slope and physical shape of graphs. This rate of change, negative 1.311 approximately, in decimal form, means that in the moment when x is 1, the y values are changing by negative 1.311 times the rate at which any x values change. So if I change x by a little bit, for any amount that I change x, y is going to change by negative 1.311 times as much. So 1.311 times as much, and in the opposite direction. Going back to like the adding candy to a box or getting gallons of gas or whatever we talked about like the second day of class, the rate of change still means the same thing. It's just that different values of x have different associated rate of change values. And this one, we found it by using a small interval. It seems reasonable for the whole interval, but if I'm using this 0.05 h value, if x were to be a little bit larger than 1, I wouldn't be using this endpoint anymore. I would be using a new endpoint based on the method we've been talking about. The sliding h interval, it kind of goes along with x. But let's talk about this function rule and doing our f of x plus h sort of stuff. Like, let's create, using some algebra, a formula that tells us the rate of change of function g for any value x, where I can plug in the values later, instead of just getting a couple example values. So take a couple minutes. Let me see if you can figure out what on earth to do with this. So g of x is this 12 over x plus 2. And my goal is to find the rate of change of function g with respect to x, or the rate of change of g of x to x, that ratio. So it's going to be some ugly sort of fractions, and some of the least favorite stuff from like college algebra or algebra 2 with weird looking fractions and denominators to deal with. Think about how to write out this r sub g of x or g prime of x for this particular function and the sorts of things we might need to do algebra-wise to simplify it. Because this is not a power function, at least not quite. So the first step in this would maybe be to write out something like this. Just filling in what is g of x plus h as opposed to g of x. Those two things are going to be subtracted in the numerator. Which at this point still it's at like, okay, now let's imagine h essentially 0. Not helpful because both the numerator and the denominator of this fraction would be essentially 0 and don't really know what that means. By the way, that situation where you have a almost 0 over almost 0 fraction where like I don't know what that means because that's a nonsense fraction if it is actually 0 over 0. 0 on the top and bottom is usually referred to what's called as an indeterminate expression, meaning you can't figure it out just now. You have to do something else, and typically it's algebra. So if I want to simplify this, it's not expanding a binomial like that x plus h squared minus x squared. There's not expanding to do, but algebra-wise, this numerator, I've got two fractions with currently not common denominators that are being subtracted. If I want to subtract them, I need a common denominator, which just the standard multiply each fraction by the other one's denominator should do the trick. So the first fraction multiplied by x plus 2 top and bottom, the second one by x plus h plus 2 top and bottom. Here's the unmultiplied out but subtracted form. We have two fractions with this same, not multiplying it out, this same denominator. The first one would have this as the numerator, the second one with this as the numerator. And those two things should be fairly easy, those numerators of the numerator, to multiply out and combine some like terms then. I'm not actually going to multiply out that common denominator. We can avoid doing that in reality. But with common denominators, just literally writing the subtraction, first numerator minus second numerator all over that common denominator, we'd get this expression. So if you can see what would be taken away. So I have a 12x in the first half minus a 12x in the second half of the numerator. Cool, those are gone. 12 times 2 minus a 12 times 2, also gone. So all that's left out of the numerator is this h and this 12 that's after the subtraction sign. So negative 12h is all that's left of the numerator of the numerator. So kind of one step away, we've got this. Now, I don't like having compound fractions. So instead of having this over h, this whole mess of a numerator that we're working on, instead of writing it divided by h, if we write it as times 1 over h, you can say I've reduced this all at once here. Here, let me see if I can write in one extra step. I thought I had an extra step written in there. Oops. So this was negative 12h over that, all times 1 over h instead of writing it as divide by h. If I rewrote it like this, you can say, oh yeah, cross-canceling, the best part of fractions. And then that's gone. And so all we've got then left is negative 12 over x plus h plus 2 times x plus 2, which I'm still not going to multiply out, because at this point, I no longer have that weird h denominator. And looking at this, I can imagine what this is turning into if h is essentially 0. The numerator is 12, and the denominator is almost the same thing twice. It's almost x plus 2 squared. So that's what I'm going to call this. As h becomes essentially 0, then this becomes negative 12 over x plus 2 squared. The closer h becomes to 0, the closer this rate of change function gets to be this right here. So I've got 12 over x plus 2, whose rate of change function is negative 12 over x plus 2 squared. It still seems kind of related, which is good. Thinking about shapes, when we had h equals 0.005, this is the result that we got, or 0.05, not 0.005. If I use this formula with the rate at 1, I get negative 12 over 3 squared, which is negative 4/3, negative 1.3 repeating. So it's pretty close, right? But let's think about other things. Let me go back to that graph for a second. Here it was. All right, so this function here, this is just showing the first quadrant portion of this. If I want to look at, let's see, so this is, I knew it was going to do that. This is g of x equals 12 over x plus, what was it, 2? Yeah. So the rate of change of function g of x is supposed to be negative 12 over x plus 2 squared. I just want to point out a couple of things about that. First of all, notice that either one of them would be undefined if x were negative 2. That's good, because if the original function were undefined there and the derivative, this rate, had a value, that would seem kind of strange. But also, notice that this function, a negative number over something squared, when it's not 0 squared as a denominator, this rate function is going to be something negative all the time. A negative over something that's guaranteed to be positive if it's not making a nonsense fraction. So thinking about this function, that should make sense that its rate of change is something always negative, both in the part that's shown here, and also if you remember what g of x looks like kind of in general, the first quadrant part looks like, well, it's not just first quadrant, it splits at negative 2. But it's like this. So from left to right, this is always going downhill, except when it's undefined and it just kind of jumps all of a sudden. But from left to right, where this function is defined, it's decreasing, which should make sense then that its rate of change function, where it's defined, always comes out to be something with a negative value. So I hope that kind of makes sense. Now the other thing I wanted to point out about this got a couple minutes, is about how this relates to power functions, because it's not actually a power function, I said, but it's actually kind of close. So we talked about power rule. Says if I have x to the n, let me just say y equals, then the derivative of y, or the rate of change of y, has a coefficient n x to the 1 lower power. Now, we had 12 over x plus 2 as our g of x function. This would be the same as, well, there's a negative power of x plus 2. If you remember some algebra trickery, this is actually the same as 12 times x plus 2 to the negative 1 power. Something in the denominator to the first power is the same as that same expression multiplied on to the numerator with a negative power. So this is negative first. So this could, there are some other variations we'll worry about more in the future, but if I want to find the rate of change of function g, if I think about this power rule here, well, I've got this coefficient, I'm just going to leave that. And I've got something to the negative 1 power. Now, I can't expand this binomial. That's not a thing you can, like, it's a negative power. I'm just going to have to stick with it like that. But if I follow what power rule said, I'd have 1 lower a power, which is 1 lower than negative 1 is negative 2. And if you see what we have here, I've got a 12 times a negative 1 and an x plus 2 to the negative 2 power. X plus 2 to the negative 2 power is also known as x plus 2 squared in the denominator. So if the denominator had been a little bit messier, this wouldn't quite work out as easily. There's something else called chain rule that we'll deal with if you have more complex things than just a linear function, linear translation of x to negative powers like that. But this is the result we got. It actually is still related to power rule. There's a lot of ways that power rule can hide its usefulness, because you can use it in a lot of cases if you just rewrite them. So on Thursday, we're going to talk about a bunch of different things that we can take derivatives of, whether you did or did not realize that you could actually do them already. We're going to add on a few more rules for things that aren't just strictly power functions. Like, for instance, they mentioned polynomials, multiple terms. That's an easy one. And a couple other short things. But we'll talk about that on Thursday. I will see you then. Oh, wait. One other thing. I almost forgot. I'm going to put this online anyway, but I photocopied copies for you. The take-home quiz will be due Thursday night via online submission on Canvas. But I wanted to give you a paper copy so that if you are going to tutoring or something between now and then, you can ask questions about this. It is a take-home quiz, so whatever resources you want to use, you're welcome to use them. There's 2 sides. Like I said, I'm going to post this document PDF form on Canvas, and then I'll also have instructions on how you're going to submit your answers to Canvas.
I took the midterm yesterday. I didn't start on homework. Yeah, either. I think it's not very hard. Thursday. Actually, I think